present his work, Difference Rewards Policy Gradients, which was published at the ARMOS conference just a couple of weeks ago, and also presented at the Adaptive and Learning Agents workshop there, which also got him the best paper award at that workshop. So without further ado, I will hand over to Jacopo.
Okay, thanks, Lucas. So thanks for the introduction. First of all, as Lucas said, this is my most recent work. It has been presented at AMAS as an extended abstract, and the full version of this paper is available online, so check it out for any details you may be interested in. Okay, this work is about difference rewards policy gradients. And other than with my two supervisors, Frans and Rahul, I also completed this work with Sam Devlin from Microsoft Research Cambridge. So, okay, I'm just introducing some background here, something that you probably already know about. That is, multi-agent reinforcement learning has been widely used in cooperative systems with a shared reward signal. One of the things that we would really like to achieve when applying reinforcement learning to multi-agent system is that of having decentralized agents that are agents that can be executed independently one from the others. This doesn't mean that they don't have to take into account the decision of the others, but just that there is no centralized controller to rely upon. And one of the techniques that has been setting itself as pretty much the standard for having decentralized agents is that of CTD, or centralized training and decentralized execution. In this framework, as you probably already know, we have a centralized training phase in which all of the agents can access the informations of the other agents, such as their observation, the action they perform, their internal state, perhaps their gradients, whatever they actually need. But then when we are in the decentralized execution phase, all of the agents are solely to rely on their own local sensing, their own local information, so that they can be executed in a purely decentralized way. And in this framework, one of the family of algorithms that has established itself as one of the most popular is that of multi-agent policy gradients. Actually, multi-agent policy gradients have been born a bit before the CTD paradigm emerged. There is a seminal work from Peshkin, date back to the 2000 here. But with this framework, it has really set itself as a standard because it allows us to train decentralized policy, so we can learn the parameters of decentralized policy, while perhaps using centralized information during the training phase as per the CTD standard. Just a couple of information on policy gradients. I suppose you already know all of those things, so I'm running pretty fast actually. The aim of policy gradients is representing a policy with a set of parameter theta. We would like to improve those parameters, to change the value of those parameter theta, so that the resulting policy, the policy that is represented with this parameter, is maximizing the expected future return for the agent. What does it mean? It simply means that the agent performs some action in the environment, it observes its own outcome, and then we adjust the value of the parameter following the gradient of this expected return. So we actually expect an improvement over this return. The same kind of reasoning has been applied to multi-agent policy gradients, in which we model all of the agents in an independent way. So each agent has got its own set of parameters, theta I, and they all independently update the value of their set of parameters according to some signal that express how good the performance was in the environment. Okay, you know that we are in a multi-agent setting, so things are not as simple as in the single-agent setting, because in single-agent setting, you probably know that we can use either the Monte Carlo return, that is simply using as an estimation of the quality of the policy, the sample return that we obtain throughout the interaction, or we can learn a critic, an additional something that is representing the value of certain action in certain situations. Things in a multi-agent settings are somehow similar but slightly different, because especially in a cooperative setting, the return signal is shared by all of the agents. So all of the agents actually perceive the same reward signal. And also, when we perhaps would like to represent a critic, we can face different possibilities. One of those, and the one that is usually used under the CTD paradigm, is critic. So a very big critic that is representing the value for all of the agent performing a specific action in a specific situation. So this is like a monolithic piece, a very big component that is learned in a centralized way, so accessing information from all of the agents, and then is not used during the execution phase. So one of the things that usually multi-agent policy gradient algorithms are not tackling is that of multi-agent credit assignment. That is, we just say that all of the agents perceive the same reward signal. That is, they're all rewarded the same at the end of a specific time step, no matter what was their real contribution to receiving that specific value. I can give you an example. In a football match, if a team is winning 4-3, that would probably mean that the forward strikers are really doing a great match. They scored even 4 different goals, actually. But the defenders perhaps are not playing that well because they still allow the opponents to score 3 goals. So, but at the end, the team won and they all receive a positive reward signal. How can all of the different players in the football team assess how their contribution led to that reward value? Because, I mean, here there is a difference. The striker really played pretty well, but the defender did not. How can we figure this out? Well, this is the problem of multi-agent credit assignment. And as I said, this is something that multi-agent policy gradient and more generally a lot of multi-agent reinforcement learning algorithms are not directly tackling. There are, of course, some algorithms specifically made to tackle this problem, and perhaps the most famous family of such algorithms is that of the so-called difference rewards algorithms. Difference rewards are indeed, as I said, a family of algorithm. So there are more different flavors to this idea of difference reward, but all of them rely on a very simple idea. That is, we would like to provide each of the agents with an individual shaped reward signal that is specifically assessing their own performance, their own contribution to the overall team outcome that they can use during the learning phase to try and improve their own performance. There is a nice property of difference reward that is showed in the Wolperton-Thumer original paper about using difference reward. And this property is that difference rewards are aligned with the original reward. What does it mean? It means that if an agent is able to increase the value of its own difference reward procedure, it will also increase the overall value of the reward, of the return for the entire team of agents. So this is a very nice property, and it's a very useful one because it just allows us to ignore the shared reward signal and come up with this sort of like shape value somehow. I'm guaranteed that if we improve for this shape signal, we are also improving for the original shared reward signal in the system. Among the various possibilities, the one that I'm focusing on, is called aristocrat utility. In aristocrat utility, each agent is somehow marginalizing out, it's like removing its own contribution, its own average contribution from the shared reward by subtracting, as I said, from the shared reward R. Here is subtracting the expectation over its own policy of the reward value that it would have obtained if, instead of performing the action that it just did, its own local action in the joint action A here, it instead performed some other action B. So it's actually marginalizing out its contribution weighted by its own policy. There are a couple of remarks here. The most important one is that applying aristocrat utility and more in general applying difference reward algorithms require complete knowledge, or at least complete access to the reward function, because we need to estimate the other reward values here in the expectation term, the second term of the right-hand side of this equation. And in order to do so, we actually need to access the reward function. And this is not something that is generally achievable in a standard reinforcement learning problem, right? I mean, in reinforcement learning, usually we do not know the reward function in advance. We can actually apply a model-based algorithm if we want to come up with the transition dynamic and the reward function, but this is something that is generally not applicable unless we are really designing the system. So if we are the designer of the system, of course, we know the reward function because we are designing that. So, I mean, but what I really wanted to give you is an example here to try and clarify how aristocrat utility is working. We have this very simple two-agent matrix game in which both agents have got two possible actions, A1 and A2. What we have is that if agent X is choosing its own action A1, no matter what agent Y decides to do, the entire team will perceive a reward of 10. So the action of agent Y in this case is influent, and the reward only depends on agent X. If instead agent X decides to perform action A2, this is where agent Y comes into play, because if at least agent Y decides to perform action A1, the overall reward will be 5, otherwise they will get a reward of 0. And let's suppose that at a specific time step, both agents are following a uniform policy, so assigning the same probability to both of their actions. And as I said, at a specific time step, they end up selecting this joint action here. So agent X choose to perform action A2, and agent Y choose to perform action A1. So the resulting reward will be 5. So here, the lower left value in the matrix. How can the agent access? How can they figure out how their specific action are really contributing toward this value? Because I mean, 5 here is not about value, right? They could also have achieved 0, but they could also have achieved 10 if agent X were choosing action A1. How can they figure out this? We can, as I said, apply aristocrat utility. For example, for agent X. What do? We simply subtract from the reward value we just obtained from the environment, so 5, the weighted, the average value of all of the other possible reward value if agent X has to play something else, weighted by its own policy. So here we are subtracting 0.5 times 10, the value that comes from agent X choosing action A1 rather than A2, plus 0.5 times 5, the value that comes from agent X playing action A2. And the overall reward is minus 2.5. So this is actually a negative value. That probably means that the agent could have done something else, resulting in a better outcome. What for agent Y? Well, we can apply the same equation, but we actually observe that the value for agent Y is now 2.5. So this is a positive value. Indeed, we would like agent Y to select action A1 as often as possible, right? Worst case scenario, agent X will be selecting A1 as well. So the decision of agent Y is not really important, doesn't really matter. But if agent X end up selecting the wrong action, at least agent Y can patch the error of agent X, and at least the whole team will perceive a reward of 5. So this should give you a basic idea of how aristocrat utility is working. There is in multi-agent reinforcement learning literature an algorithm that is combining multi-agent policy gradient with the idea of difference reward, this idea of aristocrat utility, and that algorithm is a very popular one. It's COMA, also called counterfactual multi-agent policy gradients. The basic working idea of COMA is to apply the difference in mechanism, this aristocrat utility, on the action value function Q rather than on the reward function. So here, instead of assuming the complete knowledge of the reward function as in standard difference reward methods, they are simply learning a centralized critic Q that is conditioned on the state and the joint action of the agent, And there is actually a bit more in the real implementation of COMA, but this is more than enough to actually see how it works. They learn decentralized critic, and then they are simply translating this idea of Aristotle, so this expectation over each agent policy, to compute this delta Q term here that they called counterfactual advantage function. It is indeed a sort of advantage function, because here we are subtracting a sort of value function, or at least a baseline that is non-depending on the action of the agent through the Q function. So this is actually a sort of advantage function to drive the working mechanism of the policy gradients. There are, however, some issues with COMA. COMA was a very well-designed algorithm, in my opinion, but when people is comparing to COMA, actually what we observe in literature is that usually COMA is outperformed, sometimes even by very simple baselines. So probably there are some issues. What I was thinking was that perhaps those issues reside in learning decentralized critic. Learning a centralized critic is a pretty complex problem, because it has to encapsulate and represent the values of many different joint actions. The number of joint actions, as you know, it's exponential in the number of agents. So as soon as we introduce more agents in our system, the size of our critic, the size of the input space of the critic will increase exponentially, and so thus the values that the critic have to represent. Also, other than this, learning an action value function is difficult because of bootstrapping that are introduced in the Bellman operator. So you know that to update a Q value, we also need internal estimates of other Q values. But if those estimates are not good enough, we will just learn wrong values in turn. There is also a moving target problem, that is the critic is updating itself, and as soon as it updates, also those target value will move. So the target that the network tries to achieve is always moving. You probably know that this can be eased a bit with a target network, but this is not enough. And also, final problem is that in case which the reward we have a full access in the reward function, COMA is not really exploiting this knowledge. This is not something catastrophical, but we may actually be in situation in which we have such full access. Perhaps, as I said, if we are the designer of the system, and COMA is simply wasting this knowledge. So that's why here I am proposing two algorithms, actually. The first one is named Dr.Reinforce, and this is a multi-agent policy grading algorithm combined with this idea of difference rewards. Dr.Reinforce, as I said, is working only in cases in which we have such full access to the reward function. So just in cases in which we can actually query the reward function for whatever value we need. Otherwise, given that, as I said, this is a very unlikely situation, at least it's not something that we can assume as guaranteed, we are also proposing an extension to Dr.Reinforce called Dr. Reinforcer, in which we learn a centralized reward network. We learn this in a supervised fashion, so that we can then query our reward network to ask for the reward value we need to compute the difference reward. That is then going to be combined with policy gradients. The nice thing about Dr. Reinforcer is that we are learning the reward function rather than the action value function as in COMA. There are some benefits, of course. One of these is that the reward function can be learned in a purely supervised fashion. This is just a regression problem with no moving target at all, nor any bootstrapping. So the learning problem should be a bit easier. We hope that learning the reward function result in an easier learning problem, of course, but also in better generalization capabilities. So let's start with our Dr. Reinforce. The idea is pretty simple because, as I said, we have access to the full reward function. So what we simply do is replacing the Monte Carlo return we have in standard multi-agent policy gradients with a sort of difference return that is simply defined as the discounted sum over the trajectory of difference rewards terms. So this is pretty much similar to the definition of the standard return we have in policy gradients. The idea is that each of these values, each of those difference reward values here will be different for the various agents. So this difference return here is a different signal for each policy in our team. Okay, that's it. Of course, the difference reward terms here are computed with some difference reward algorithm. We choose to apply aristocrat utility. So this is pretty much identical to the question we saw before. The main benefit of this is that this value here are aligned, as I say, to the real reward. So the entire sum of those terms here is aligned with the true return of the system. So agents following this value here will also improve the overall, the share reward, the share return for the team. So they are still like improving for the common signal. What we do with this is simply replacing this, as I said, the definition of basic multi-agent policy gradients, and what we get is an individual agent, an individual gradient for each of the agents. What are the benefits of this? First of all, as I said, this is an individual signal for the gradients of each agent. So each agent is learning from an individual signal that should assess their own specific contribution to the environment. And the nice thing we found out, that is also available in the full paper, is that using our difference return here corresponds to subtracting an unbiased baseline to the standard Monte Carlo return. So on one end, we are hopefully speeding up the learning process of the agents, because each agent is now observing an individual signal, but we are also reducing the variance of such gradient because we are subtracting an unbiased baseline from the Monte Carlo return. So the benefits should be twofold. And we also have a proof of convergence for this algorithm, convergence to a local optimum. This is something not novel in multi-agent policy gradient algorithms, actually, but it's nice to see that at the very least we have some theoretical guarantees that this thing is really working. And okay, this was for situation in which we have access to the reward function, but what if we don't have such access? Well, this is where Dr.Reinforce comes into play, because as I said, the only difference between Dr.Reinforce and Dr.Reinforce is the addition of the centralized reward network R here that is learned in a supervised fashion against the sample reward that you obtain from the environment. So there is no need for any additional interaction with the environment, nor any additional simulation, nothing. The agent just interacts with the environment, they observe the reward value that they got for their agent action, and we are simply learning this network against those values here. The algorithm is pretty much done, because the only difference is then that we are replacing difference reward values computed with the reward network rather than by querying the true reward function. So we are just redefining our difference reward term here by using to use our reward network R here. So the idea is pretty much identical. We are just exploiting this knowledge that we are building together with the policy rather than assuming full access to the reward function. And okay, we just have got some preliminary experiments on two fairly easy classical converting benchmarks. The first one is called multi-rover. Multi-rover, we have a set of landmarks over a grid board, and we would like each agent to go and cover one of the landmarks, no matter which one. We just want all of the landmarks to be covered by the end of the episode. While the second problem is a variation to the classical predator-prey one. Actually, here we have a random moving prey, and each of the agents have got a catch range let's call it this way, of one cell ahead and in each direction. We would like all of the agents to swarm on the prey and stay on top of it for as long as possible. And what are we comparing against? We are comparing against COMA, of course. That seems fairly obvious as a state-of-the-art algorithm. We are also comparing against some other standard multi-gene policy gradient baselines. We are comparing against individual policy gradients, and we are comparing against centralized critic actor critic method. And finally, we are also comparing against proper difference reward methods, the one from this paper from Colby et al. From 2014. This algorithm was actually working with evolutionary techniques, so we had to slightly adapt it to work with policy gradients in order to keep our comparison fair. But this one here, the main point is that it's using a slightly different formulation of difference reward. Is based on another algorithm from that family. This one is also concerned with learning the reward. So this is also a comparison of our reward network, so our centralized reward network, against the mechanism used in this algorithm. Let me show you some results. Those are the results on the multi-reward problem. We can see how with just 3 agents here on the left plot, both COMA and Dr.Reinforcer, so the version with the learn reward network, are doing fairly well. They are almost matching up with Dr.Reinforce. Dr.Reinforce is the green line, and is the one above all of the others. What can we observe from this? We can observe that, of course, accessing the full reward function is beneficial. That seems obvious. But also that, at the very least, in fairly simple problems, Dr.Reinforcer is capable of matching up with this, let's call it like a super version, like this is actually an upper bound. Dr.Reinforcer is an upper bound to Dr.Reinforcer performance, because it just gives us the performance that we will get with Dr.Reinforcer in case the reward network just converge perfectly to the true reward function. So given that the gap is fairly small in this setting, this actually means that our approach is at least applicable, that we can fairly well learn a reward network. Well, we are also doing pretty much on par with COMA. So far, so good. This means that also COMA is capable of solving this one. What for the other baselines? Well, we can see how the other difference reward algorithm is not really doing great. More generally, not any of the other baseline is performing on par with COMA and our algorithms. So at least this proves that our difference reward mechanism is beneficial in some way to the policy gradients. But then things get a bit worse when we move to 8 agents, because we can see how Dr.Reinforce is still doing fairly well, is still achieving a fairly high return. Here, all of the values are negative because agents are rewarded with the distance from the landmarks. So the closer they get, the higher reward they will get. But we can also see how nor COMA nor our Dr.Reinforcer are capable of achieving anything useful. We can see how, to be very honest, Dr.Reinforcer is doing slightly better than COMA, but they are both doing fairly worse than Dr.Reinforce alone. So probably something went on with both the learning of the critic and the learning of the reward function. This actually highlights that even learning the reward function, even if that is a simple regression problem, is not as easy as it may seem, and it actually requires some careful consideration in order to achieve a good reward function. Well, things are a bit different for predator-prey, because when we just have 3 agents, all of the algorithms are pretty much doing fairly well. We can see that Dr.Reinforcer is doing better than COMA and perfectly on par with its upper bound. But even when we now have 8 different agents, the performance of the baselines are drastically reduced. COMA is not actually even able to learn anything useful here. It's just capable of achieving a very low reward. But our Dr.Reinforcer is still doing pretty much as well as Dr.Reinforce. There is a bit of variance here. That's fine because the reward function with 8 agents starts out to be fairly big. But we can see how this idea is also generally, this idea of learning a centralized reward network is also applicable, and it can actually provide us with good results with fairly honest sized multi-agent systems. A bit of analysis here because we were interested in seeing how easier it is to learn our reward network rather than the centralized critic as in COMA. So what we did here, we have been sampling state action pairs following trajectory given by other algorithms. So we have been executing the other baselines and also some uniform sampling and some random sampling, whatever, on the two problems, collecting state action pairs. And then we asked the reward network and the centralized critic in COMA to predict respectively the reward value and the action value. And then we compared those two values to ground truth. So to the true reward function and the true action value function given a certain policy. And what we observed is that, for example, here on the multi-rover problem, the prediction error, the PE of the reward network is increasing with the number of agents, is scaling in a linear way, but it's always fairly small, while the prediction error of COMA critic is higher, especially with more agents, with 5 and 8 agents. So this could be the reason for which COMA was not convergent, even if it gets a bit higher, even with the reward network. And if we move to the predator-prey problem, things are actually a bit puzzling at first, because we can see that while our reward network is doing fairly well with all of the possible settings, this actually can explain the good performance of Dr.Reinforcer, COMA critic is doing a weird thing because it results in a very high error with just 3 agents, and then the error actually reduced. And this was actually a bit puzzling for me at first, but the explanation I got for this was that COMA critic overfitted so much to the situation in which none of the agent is on the prey, so not achieving any reward at all, that is just committing less error by predicting always a value very close to 0, rather than trying to predict the true action value function. Okay, except for this value, why are we interested in this analysis? Well, this is because both our reward network and COMA critic are faced with a situation in which they have to predict values for state action pairs that they have never been trained on. This actually gets back to how difference reward is computed, right? You are marginalizing out the policy of the agent, so you're actually changing the local action of the agents in order to compute that second term in the aristocrat utility definition. This may actually require you to predict values for state action pairs that you never encountered. So we actually really need those two networks to be capable of generalizing very well beyond the training sample that they have been trained on. And this is actually crucial, because otherwise we will just get totally off prediction, and the signal that we are using with the policy gradients will be totally wrong. And the interesting thing in this analysis is that we see how the reward network is, in general, capable of predicting values that are fairly correct, while COMA critic, in many cases, is not. Because, of course, as I said at the beginning, learning the action value function really seems to be a more difficult problem. So I would like to conclude. Here we are presenting, we present Dr.Reinforce, that is combining multi-agent policy gradients with a difference reward mechanism. And this algorithm has been able to outperform COMA and other baselines where in cases in which the reward function is known. And we also presented a practical version called Dr.Reinforcer, that works by learning an additional reward network for cases in which we don't have such access to the overall reward function. And finally, we also analyzed our learning this centralized reward network seems to be an easier problem rather than learning a centralized critic, resulting in a lower prediction error and in turn in a better generalization. That's it. Yeah, thanks for listening.
Thank you very much for that presentation, Jacopo. Yeah, I would hand over to questions for